the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through vectors and vector equations. You should have just completed a review of vectors, and we're going to go ahead and continue forward with a little theorem on the arithmetic properties of vectors in Rn. And that's all this video is going to be dedicated to, is just introducing this theorem and maybe proving one of the properties. So here are the properties. We're going to let u, v, and w just be vectors in Rn, and c and d will be scalars from the real number system. The following vector properties are extensions of the axiomatic basis of the real number system. That is, these are just the rules that we use to play mathematics, and they should be hauntingly familiar from your arithmetic course many years ago. So we have the commutative property of addition for vectors. That's kind of a nice clean one. Let's go ahead and write that down. So u plus v, if vectors u plus v, that's the same thing as the vector v plus the vector u. All right, what else do we have? Well, we have the associative property of addition for vectors, and that just means we can associate the addition any which way we want. That is, the quantity of the vectors u plus v and then plus w is the same thing as u plus the quantity of the sum of vectors v plus w. Again, these should look very simple and familiar to you from your good old arithmetic course. Of course, this is not arithmetic, this is vector arithmetic, not scalar arithmetic. Then we have the additive identity of vectors. Well, this just basically means there is a vector in Rn such that v plus that vector is always going to return v itself. And that vector is traditionally called 0. It's the 0 vector. And in arithmetic, 0 is also the additive identity, right? Any number plus 0 is the original number. That's why we call it the additive identity. And just like in arithmetic, when you have a number, you can add its negative so that you get 0. You have the same thing with vectors. It's called the additive inverse of vectors property. And this basically just tells us for every vector v in Rn, there should be some other vector called opposite of v, such that when you add it to v, it becomes the additive identity. Again, most of these are going to be very simple and familiar to you. Now I'm going to pause right there because the rest of these actually involve scalars. And I want to just mention something here because a lot of students take these for granted. And that's mainly because they're so familiar to you. And that's totally okay. It gives you a very natural understanding of vector arithmetic. However, your scalar arithmetic that you grew up with does not apply to all vector operations. For example, there's no such thing that we have right now called vector multiplication. So there's not a u times v in this list. Moreover, unlike what you would do in arithmetic, you are expected to be able to prove these. And that's why I'm going to showcase the proof of one of them in this video so that you get an idea of what a proof of one of these looks like. It's actually not bad. It just requires a little bit of patience and being able to step back away from the complexities of mathematics into a very simple style of mathematics where you take your time and take baby steps and justify everything you do. That being said, let's go ahead and finish all this stuff up. So we have the scalar distributive properties onto vectors, and notice I pluralized the word properties. It's because there are two of these properties. So the first one is commonly the group C plus D times a vector V. Well, that's the same thing as C times the vector plus D times the vector. And then the second scalar distributive property onto vectors is when you have two vectors and one scalar. And again, that's pretty obvious to most people, but again, you're going to have to prove these. Let's see, we have the scalar associativity property of multiplication with a vector. That's just a name that I wrote down that's very bulky, but it really just means that if you have a couple scalars and you want to multiply them and then multiply them against the vector, that's the same thing as taking the second scalar and multiplying it against the vector and then multiplying that by the first scalar c. And that's the same as taking the first scalar and multiplying it against the vector v and then multiplying that against the scalar d. So these are just the scalar associative properties of multiplication with a vector. And finally, we have the multiplicative identity of vectors. And this is essentially just a number, basically a scalar, that we're going to multiply by a vector so that it becomes the original vector again. Well, that's obviously 1. 1 times any vector is the vector itself. There are smaller properties that I'm not mentioning here, like 0, the number or scalar 0 times a vector is just the 0 vector. I'm not mentioning that in this video, but let's go ahead and prove just one of these. I'm going to look through very quickly and find the one that I like to prove. Let's go ahead and prove this guy right here, because it not only involves vectors, but also a scalar. And it's very important to outline your proof very cleanly. So I'm going to state it as a theorem, and then we're going to start the proof. All right, there's the theorem that we want to prove given a scalar in the real number system and two vectors, u and v, in Rn. There we go. C times u plus v is the same thing as cu plus cv. A little aside before I begin, it turns out that all of these properties hold under the complex number system as well, but generally with linear algebra, you're just working in the real number system. However, like I said, you could also apply these properties over the complex numbers. So don't get too stuck on this being the real number system. It doesn't have to be. So starting my proof, I'm going to use a different color pen for this just to really showcase that we're starting the proof. And to be very rigorous, I'm going to state what we were given. Now you could probably tell I did some adjusting on that as I was writing it down, just because I want to really start my proof by saying, suppose we have, or let C be a scalar from the real number system and U and V be vectors from Rn. And then we can go ahead and start with either the left or the right-hand side of this equation, but not assuming this equation is true. We're going to start either with the left or the right. It really doesn't matter to me. I'll just start with the left-hand side. Now you're going to use the fact that u and v are vectors in Rn. So right now I'm going to go ahead and do that. Notice I didn't use any theorems here or anything like that. Right now, all I'm just doing is writing a different notation for the vectors. So this is kind of the vector notation, and this is the list notation, or what is often called the matrix notation of a vector. So we have that written out there, nothing really special. But one thing we do know about vectors themselves is we know we have vector addition. We know how vector addition works, and we know how scalar multiplication works. What you do not want to do in a proof like this is two things at once. Really, early on in linear algebra, doing a bunch of things at the same time is a big fat no-no. You want to showcase that you have the patience to step by step go through a problem. So I'll go ahead and take care of the vector addition right now. And your instructor might require you to say something like vector addition or something like that to state that that's how you know the sum of those two vectors becomes the single vector. However, if you're one of my students, I don't really require that amount of detail. I just require you to show this single little step here. Now we happen to know that a scalar times a vector, well, that just scales every entry of the vector by the scalar itself. So I'm going to go ahead and take that scalar and apply it to each of the entries inside our vector. Now I'm going to pause here for a moment because I want you to notice something. I did not just pull that scalar in and immediately distribute it to u sub 1 and v sub 1 and u sub 2 and v sub 2 and so on and so forth. Right now, I'm just using one property at a time. The scalar multiple of a vector is the vector where every entry has been scaled by that scalar multiple. Now I can rely upon my old school arithmetic by zooming into this vector and pretending as though I'm not working on a vector, but instead just on regular old scalars. So I can always use my knowledge of arithmetic once I'm inside a vector structure. So at this point, now that I'm inside, I can take advantage of distribution properties and stuff like that, because these inside are just scalars. I've known scalar properties since childhood, so it's not a big deal for me to say, oh, this is the same thing as CU1 plus CV1, CU2 plus CV2, and so on and so forth. Now let's go ahead and pause and go up and take a look at where we want to arrive. I want to arrive at the sum of two vectors, C times U plus C times V. So I somehow need to break apart this single vector into the sum of two vectors. Luckily, I can do that. We happen to have a property of vector addition, so we can do the opposite of vector addition and say, okay, well, if I have a single vector where each of its entries are just a sum of two numbers, I can break that into the sum of two vectors. And like I mentioned before, you might have an instructor that requires you to state this is by the vector addition property. If that's the case, you just want to state that off to the right here, vector addition property. Now we're going to go ahead and take advantage of scalar multiplication of vectors. So notice each entry in this vector is being multiplied by the scalar c. That's the same thing as c times the vector u1, u2, all the way to un. And same thing with this second vector. So let me go ahead and do that. And now that we've got to this point right here, we know u1 through un is the vector u, and v1 through vn is the vector v. And lo and behold, we have arrived at the right-hand side, which is what we wanted to arrive at. C times the quantity u plus v, we have proven, is actually the same as cu plus cv. All of your proofs for the arithmetic properties of vectors go along the lines of this proof. It's very, very similar. You write them in their component forms, and then you do these types of component by component addition, that type of thing. Notice I was very patient with the baby steps here. It's very important that you do that. Don't do two things at once. When you're early on in linear algebra, it is illegal to do multiple things at once because we really need to see that you can slow down, take your time, and go through a process. Now, before I leave this video, I just want to mention a couple notes. The first thing is that the multiplicative laws for vectors are conspicuously missing from that list. That is, I did not have a property that said, oh, guess what? U times V is something. There's no such thing as U times V when you have vectors. So that property cannot exist. So not everything from arithmetic immediately comes over to the arithmetic of vectors as well. We're missing a lot, actually. The second thing I want to note, and I've already mentioned this, these properties hold over the complex number system as well. So that's just something that you're not going to really deal with in linear algebra unless you're taking a linear algebra that's been combined with a differential equations course. Then it is very possible, and in fact very likely, that you're going to work over the complex number system at some point, especially when you do signal analysis. But that's all I wanted to do in this video. Notice I didn't do any examples because honestly, doing arithmetic with vectors is pretty low levels. You guys should be able to do it. I trust you. All right. So I hope this video was somewhat helpful. The main point was for you to recognize the level of detail you need to have when doing a proof for these types of properties. I hope to see you in future videos. Have a great day and be wonderful human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.